In this lecture, we're going to see a couple of factorization methods. Both of them are meant to be attacks against RSA. One of them is generic, and the other one only works when the exponents satisfy certain properties. So let's start with a generic one, and it's called Pollard's row algorithm. And the reason why it's called row algorithm is going to will become clear in a few slides. The objective here, of course, is to factor the public modulus, the public RSA modulus, which is of the form p times q for secret p's and for secret primes p and q. So the general idea is that we would like to have x and y different than each other, such that x squared is congruent to y squared mod n. If that happens, then we have the relationship that n divides x squared minus y squared, and that factors as x minus y, x plus y. So what it means is that with good probability, we're going to have that either p divides x minus y and q divides x plus y, or vice versa. The idea behind it is that in either way, the GCD between n and x minus y is going to yield one of the factors of n. And GCDs, of course, are easy to calculate. So if this equation is solved, then it means that we have a good probability of finding a non-trivial factor of n. So what I mean by that is not 1 or n. And so it will be either p or q that we find, and then that solves the problem. So for that, we use Pollard's row method is really an application of Floyd's method for finding collisions. So let's see what it means from this higher perspective. So we assume here that we have a function that's a polynomial p is equal to ax squared plus b. Then finding our equation x squared congruent to y squared mod n really is the same as finding two elements xi and xj, such that the polynomial evaluated at xi is congruent to the polynomial evaluated at xj mod n. Now, it seems it's in fact what we really need is the more likely congruence, which is that p of xi is congruent to p of xj mod p, where p is one of the two factors of n. And in this case, you can easily see that the GCD of xi minus xj and n is going to yield p or q. So Floyd's algorithm finds collisions in a sequence that is defined by n sub I plus 1 equals f of ni. So in this case, what will play the role of n is this degree 2 polynomial p, but Floyd's algorithm is a more general algorithm that would work for other families of functions. Okay, so let's see how Floyd's method works. So first of all, we sort of specify Floyd's method for the case of f of x equals p of x mod p, where p is one of the secret divisors of n. Now, what's interesting here is that I'm defining a function that I'm not capable of evaluating because it would require for me to know p, which is precise p, small p, the prime divisor of n, that I'm actually trying to calculate. But let's just sweep that under the rug for a moment, and then we'll get back to that later. So the basic idea is that we're going to define two sequences, one of them defined by x sub I plus 1 equals f of x, and the other one, y sub I plus 1 is f of y. So one is going at twice the pace as the other. They both originate at the same point, and we continue until one of them, until we have an index such that they collide. And if that happens, of course, we do have our relationship p of x is congruent to P of y mod P for x equals x sub n minus 1 and y equals f of yn minus 1. So in this case, the idea is if two people are running on a track and one of them is running at twice the pace as the other one, well, the idea is the one who's running at twice the pace is going to catch up with the slower runner. Now, because we're talking about a discrete sequence, we have to prove formally that, well, first of all, this collision is going to happen within a reasonable time, and second, that the runner that runs at twice the pace is not going to leapfrog the slower runner. Theoretically, there's no guarantee that it happens. So here's how we find the collision. So this is the sequence xi. So starting at x0, then f of x, and then f of x0, f of x0, and so on and so forth. So the reason why it's called a row algorithm is because starting at an index t, which is the smallest for which we have an overlap between xi and xi plus t, and we know that this will happen because we have only a finite amount of possible nodes, p to be precise. So we know that at some point we're going to loop back, and once we start looping, then we have to stay in the loop. So this is the first index here. We denote it by t as the first index for which we have two xi's that collide. And then from there on, we have to hit only nodes that have previously been hit. Okay, so that has the shape of a row. And now we have to see the behavior of the two sequences inside this row and see if we can prove, well, as I said, A, that they do collide at some point, and B, that they do collide with an interesting bound on the number of steps. So the proposition that we're going to prove is that in fact they do collide after at most t plus l steps. Okay, so t plus l here, the best bound we know on t plus l is that it's going to be less than p. Okay, so less than the total number of nodes, which is not a guarantee, again, because there's always theoretically there's always a chance that the faster sequence could potentially keep leapfrogging the smaller sequence, the slower ones. So here's the proof. We are going to denote by j the index, which is t minus t mod l plus l. So why that index is important is because, first of all, it's greater or equal than t. So that's one thing. So what it means is that it's in the loop. And then it's also, L is a divisor of J. So the reason how we can see that, of course, is that this thing is divisible by by L, and this is divisible by L as well. Okay, so why this is important is because then what it means is where we have is that x2j and xj are in the same spot in the loop, because we have that 2j minus j equals j, and j is divisible by L. So what it means is the difference between, this is the loop, and let's say this is x2j, then the difference, the number of times that I have to rewind is exactly, to get on xj is exactly a multiple of L. So it has to be that xj and x2j are in the same spot. So here is our collision. So since we have collision, we know that this solves our problem. The only thing here that we still need to clarify, and that's something that I said before, is that we technically do not calculate f of x, which is p of x mod lowercase p, the divisor of n. So how can we possibly check that x sub n equals y sub n without calculating those values? Well, we keep, in fact, the sequences that we keep track of is not p of x mod p, but p of x mod n. Okay, and of course for y is we keep track of p of y mod n instead of mod p. Normally we would like to have a p here, but we do not know how to calculate this. So instead we calculate mod n, and of course we originate at the same spot. And then to check if x sub n equals y sub n, we just calculate the GCD of the difference between x sub n and y sub n and n. And if it yields a non-trivial factor, then we win. So this way we can calculate our result without having to calculate each term of the sequence. Now let's try this on an example. So we start at x0 equals y0 equals 2 and p of x equals x squared minus 1. So we have x1 equals 3 and y1 equals 8, and the GCD of x1 minus y1 and n equals 1, then x1 equals 8, which is normal because it's f of x1, f of x was x0, sorry, and that was x2, and then y2 equals 3968. Here again, it doesn't yield any factor. Then x3 equals 63, and y3 equals 6081, and here again we do not find any non-trivial factor. Then with x4, unsurprisingly, we recover a y2 because it's f of x0. So here you notice that this comes here and this comes here, and then y4 equals 2100, and we do not find any factor here. And then finally x5 equals 5318, and y5 equals 6579, and in this case the GCD of x5 minus y5 and n equals 97, and that gives us the two factors 97 and 97 n divided by 97, which is 83. So we find our two factors here. So that's how it works. It's a pretty straightforward method. Now let's move on to another factoring method, this time that is not generic, but it can work a lot faster. So previous method would work in time proportional to p, and statistically more like proportional to square root p if we are only interested in probabilistic result. It's due to the birthday paradox. We find a collision in 50% chance to find a collision when we try only square root of the number of possible evaluation of our function, just like finding a collision with a hash function. Now the low exponent attack works a lot faster, but it's restricted in its scope, which is fortunate for people using RSA. Otherwise we would not be using RSA. So it works when the secret exponent d is too low, which is something you don't necessarily see as a public user, but you can try the low exponent attack and see what happens. So it will be too low if d is less than the fourth root of n mod 3, over 3. Now there's another implicit condition here, is that the q and p have roughly the same size, which is, to be more specific, q less than p less than 2q. Okay, if you have unbalanced P and Q's, then you're looking at other kinds of issues. So it's not an unreasonable assumption. Now we assume that since E and D are inverse of each other mod phi of n, which is p minus 1 q minus 1, we let k be such that ED equals 1 plus k times p minus 1 q minus 1. Now we know that we can show that E over n, which is public parameter, is very close to k over d, which is private, and d is actually what we're trying to calculate. So so what we do is we compute the continued fraction expansion of E over n, and it's just so happens to contain k over d. And on top of containing k over d, what's interesting about it is that the k and d are co-prime. So k over d, regardless of the value of k, will readily give you d. The reason why is because we know that ed minus k times p minus 1 q minus 1 equals 1. So this identity directly implies that k and d are co-prime, okay, because a common divisor of k and d would have to divide 1. So that means that if I give you k over d, it gives you right away d, okay? The first step is to argue that E over n and k over d are close. So the first identity that we have here is that kn minus ed equals kn minus k phi of n minus 1, which is strictly less than kn minus k phi of n, and then here we factor by k. Okay, so we set that aside, and we have that n minus phi n is when we expand the expression of phi n, it equals pq minus pq minus p minus q plus 1, which is less than, which equals p plus q minus 1. And because of the restrictions on p and q, namely that p is less than 2q, then it's less than 3q, and because q is less than p, q is more than p, we have less than p, we have that it's like less than 3 times square root of n to the 1/2. Okay, so we keep that. And then phi of n times k, if we substitute, so we have that phi of n times k equals ed minus 1, which is less than ed, and by the restriction on d that we have is less than the 4th root of n over 3 times phi of n. Now we simplify on both sides by so we can keep that, and we'll simplify on both sides to get a relationship on k. So k in this case is less than 4th root of n over 3, and we remember our first identity here, and we have kn minus ed is less than kn minus phi n, and then we know how to bound n minus phi n by 3 times square root of n, so we replace it here, and that it's in itself, because of the bound that we have on k, is less than 4th root of n over 3 times 3 square root of n, which is the n to the 3/4. Now we divide everything by nd, and we get the identity k over d minus e over n is less than 1 over d times n to the 1/4. Now we have a bound on d, which we knew from the beginning that it was less than the 4th root of n over 3, and then that gives us that 1 over d here, the 1 over d to the n times n to the 1/4 is less than 1 over 2 to d squared. So that's the final identity that we have, and that's really what we care about, is that the difference between e over n, the absolute value of the difference between e over n and k over d is less than 1 over 2 d squared. And what it means, there is a lemma that tells us that k over d has to be one of the convergents of the continued fraction expansion of e over n. So let's move on to describing what it is to compute the continued fraction expansion of e over n, which again, remember, these are public parameters. So we know that one of the terms is going to be k over d. So the continued fraction of a real number is a sequence that starts with the floor of x, and we know that then x equals its floor plus a fractional part, and this is a fraction in itself. So a0 is equals p0 over q0. It's a fraction that sort of approximates x. It's a rough approximation, but it's by a fraction, but it's still an approximation. Now we can refine that approximation by taking a1 to be 1 over the floor of 1 over epsilon 0, where again epsilon 0 is the fractional part of x, and to write down 1 over epsilon 0 equals a1 plus epsilon 1, where epsilon 1 is a new fractional part, this time of 1 over epsilon 0, and it means that x now is approximated by the fraction a0 plus 1 over a1, which is a fraction. Okay, this time it's a fraction that may not be trivial, and we call that p1 over q1. And then we can iterate that process, taking the floor of 1 over epsilon 1 and writing down 1 over epsilon 1 as its integer part plus a fractional part epsilon 2. And then we have this new approximation of x, which is a0 plus 1 over a1 plus 1 over a2. Okay, so again, this is another fraction, and it keeps approximating x. And we call these the convergents. And one of them has to be k over d. So we need to compute them until we get k over d. Now, here's the thing. We have to decide which of these fractions is k over d. But there is no obvious test that will tell you that a given a over b is k over d, or not just something else, because we have no reason to believe, we have no way to test, for example, if d, which is the private exponent, times e, which is public, is congruent to 1 mod phi of n, which we don't know how to calculate. So instead, we have to use a trick. So we calculate for every candidate a over b, we calculate e times b minus 1 over a. And it turns out that if we had a over b equals 1 over k over d, then c would be phi of n. But here again, phi of n, we don't really know what it is, so that alone doesn't tell you. It is not alone a test of validity, because if I give you n and a c, you do not know how to check that c equals phi of n. However, we can calculate the polynomial p of x equals x squared minus n minus c plus 1x plus n. And in the case that c equals phi of n, that polynomial is in fact p of x equals x minus p times x minus q. And that polynomial I know how to calculate if somebody gives me n and c, and I know how to calculate its roots. And if the roots exist, first of all, and if I find roots, I multiply those roots, and if the product equals n, then it means I factored n and I broke the crypto system. Okay, so we are going to see how this works on an example. So the idea here is to start with e over n. And so the first convergence is always same, it's always 0. Okay, so because e over n is less than, so e over n is x, and then we have that a0 equals the floor of x, which in this case is 0. So p0 over q0 equals 0. Okay, there is nothing to test here. Okay. Now, epsilon 0, on the other hand, is 0.2839. Okay, and something. So now 1 over epsilon 0 is approximately 3 times 52139. Okay, so here we get, so that's 3 plus epsilon 1, where epsilon 1 is 0.52139. And so we get our first convergent, non-trivial convergence. So we have P1 over Q1 equals 1 over 3. Okay. So we test, we have the polynomial P of x that equals x squared minus 16,048 x plus n, so 10, 83, 71, and we find no roots. I mean, no integer roots. Okay, so we move on. So 1 over epsilon 1 is approximately 1.9179. Okay, so that's 1 plus epsilon 2, and we find that P2 over Q2 now is 1 over 3 plus 1 over 1, so that's 1/4, and the new P of x becomes x squared plus 14,727 x plus, still the same, 10,8371, and again, no roots, no integer roots to report. Okay, so now we have 1 over epsilon 2 is approximately 1.0894, which is 1 plus epsilon 3. And now that gives us P3 over Q3, which is 1 over 3 plus 1 over 1 plus 1, which is equal to 2 over 7. And now my polynomial here is P of x equals x squared minus 660x plus n, which is still 10,8371. And now the roots are 307 and 352. And of course, quick check, these two, the multiplication of these two numbers gives you n. So we factored n, and from well, we know that we factored n, so we know that 7 has to equal d. And we solve our problem. We found the private key from the public key. So that was the example of how to run the low exponent attack. And again, I want to stress the fact that it has limited scope, because if not, then its complexity is it's proportional to log n. Okay, and this is much more efficient than the Pollard's row method. So it's very efficient, and in fact, it would be a total break if it were applicable all the time.